I have two goals in this video. One is to extend the basic principles, that is Newton's second law, conservation of mass, conservation of energy principles, to infinitesimally small control volumes. Up until this point, we've been looking at macroscopic control volumes, but now we're going to look at control volumes where we essentially shrink the control volume to a point, and this leads to what are called differential analysis. And the second goal is to introduce the notion of a fluid acceleration, right? So these are two things we hope to accomplish with this video. Again, the motivation for this is depending on the nature of the problem you are interested in. Let's say you're looking at the problem of fuel injecting into a combustion chamber, mixing takes place, and then the products of combustion are ejected through a nozzle perhaps, and so you're able to generate thrust and make the system move in a certain direction. So this kind of analysis we can do with a global control volume analysis, where we take the entire combustion chamber for analysis purposes. We don't worry about the details of what's going on inside. However, there are many problems in engineering where we really have to worry about the details of what's going on in the inside. For instance, how is the fuel injected? Is the spray going to have sufficient droplets? How is the air going to come around and swirl around and mix this fuel? All that may be very important. So if I want to answer more detailed questions, I need to have appropriate tools. And that's what this accomplishes, extending the basic principles to differential analysis, where these control volumes are essentially shrinking to points in space. All right, and the difficulty, of course, is the resulting equations turn out to be partial differential equations in general. And so typically the solution is obtained via analytical methods, computational or experimental methods. Analytical methods, as I will comment again, is extremely restricted. Very few problems are in fluid dynamics are amenable to analytical solution methods. So pretty much we got to resort to computational methods or experimental or empirical methods to make progress. So let's look at the basic principles applied to an infinitesimal control volume, and we'll focus in this video on the conservation of mass principle. So we have an inertial coordinate system XYZ attached to the ground, let's say, and let's imagine we have this control volume in space shown in the sketch of dimension dx dy dz, and essentially we will shrink dx dy dz to 0. So this macroscopic control volume, what looks macroscopic in this diagram, essentially shrinks to a point in space. Let's ask the question, if I want to apply conservation of mass to this, let's ask the question, what is the rate at which mass comes out of this surface? So in other words, we need this rho UA on this surface, or rho Q for this surface, rho being the density, Q being the volume flow rate, and U being the X component of velocity. All right. So if I focus on that, I can take the property rho U, rho is density, U is velocity. These are continuous functions of position in space. That might be the value of the center of the domain. And since I'm reaching the right face of the domain, which is at a distance dx over 2 from the center, I need to take the rate of change of rho U with respect to x, multiply that by the change in x, which is dx over 2. This gets me the value of rho U at the right face. So once I have the value of rho U at the right face, I need to multiply that by the area of the right phase, which is evident from this diagram. It's simply dz times dy. dy times dz, right? So same idea. This is outflow rate of mass, and let's look at the inflow rate. So the inflow occurs on the left end of the domain. Same principles as before, except the distance I go from the center to the left face is negative dx over 2, and that explains this negative sign over here, right? And of course, we got mass flow in the other directions as well, which for simplicity, I'm not showing them on this diagram. I'm only focusing on the x direction, but you can very well imagine the same concept can be extended to the other two directions as well. Then the question is, what is the rate of change of mass inside the control volume? So how can I write down d dt of the integral of rho dv, which is what appears as the time derivative term when I look at the macroscopic control volume analysis, right? So in this case, dv is simply the volume of this element, which is simply dx dy dz. And then that multiplied by rho gives me the mass. So this term simply becomes partial with respect to t of the quantity rho dx dy dz. All right, so let's go to the next slide. So we got conservation of mass written for a macroscopic control volume shown here. And now we can apply it to this problem where for this differential fluid element, this term simplifies to this. And notice over here, I'll pull the dx dy dz out of my time derivative because that doesn't change, and only density could potentially change. And then I have the outflow rate of mass. This is on the right face on the previous diagram, and the area vector is pointing in the positive x direction, same direction as velocity. So the dot product is going to be positive, and that's what I got here. The dot product is positive, right? And then the right face is at a distance dx over 2 plus dx over 2 from the center, and then minus the inflow rate, which is this quantity, which I explained in the previous diagram. And this has to equal essentially 0, right? And of course, these two terms cancel out. And then this term and the negative of these two terms add up, and the dx over 2 simply becomes dx. And once that happens, then I can divide or cancel out dx dy dz on both sides of the equation. And what I'm left with is this form of the equation, right? So rate of change of density plus the gradient of the product rho u equals 0 is what it tells me, right? So in general, you could have mass flow in all three directions, velocities in all three directions. You're going to get what's called the conservation of mass, also known as the continuity equation, when it's written in this differential form. So this is the rate of change of density with respect to time, keeping position fixed. And these are the net outflow minus inflow rate of mass across surfaces in the x direction, y direction, and z direction respectively. And these are quantities per unit mass, because remember, I've divided a per unit volume because I've divided out dx dy dz previously. Okay, and so this form of the equation is really related to this form of the equation, and I want you to be able to see the connection between these two. So this term becomes this one right here, and this term becomes essentially the sum of these three terms together. And in general, if I have a generic coordinate system, not necessarily a Cartesian XYZ coordinate system, I use the symbol del dot rho v. And so the advantage of this is I can write the continuity equation in a very compact form. The del operator in our Cartesian coordinate system is defined as, remember this is my defining equation, delta is defined as, is how I read this, is I hat ddx, j hat ddy, and k hat ddz. So this is an operator, and it by itself it doesn't make sense unless it operates on something. In this case, there's a dot product operation at the rho v, which is what gives me this result. And of course, if you have steady flow, then the time derivative term is 0. Or if you have incompressible flow, in which case density is a constant and the time derivative term would vanish. And then this equation would simplify, the density can be taken out, and simply I have ddx of u, ddy of v, and ddz of w. The sum have to be equal to 0, right? So the conservation of mass will simplify to simply del dot v equals 0 for incompressible flow. Another way of saying that is the volumetric dilatation rate. That's what this del dot v represents, equals 0. Or another way of saying that is the velocity field, because v is a velocity and it's a velocity field, is divergence free. In other words, I take the del dotted with v, the result is equal to 0. In the case of a cylindrical coordinate system, that may be relevant in a particular application. All I need to do is look up what the del operator is in a cylindrical coordinate system, and ER, E theta, and EZ hats are unit vectors along the R theta and Z directions, and likewise the I hat, J hat, and K hat are the unit vectors along the X, Y, and Z directions that I failed to mention a little earlier. All right, so the conservation of mass equation reduces to the continuity equation. So that's a summary for the first objective that I had for this video. The second objective is to introduce the notion of what's called the material or the substantial derivative. So if I have a general velocity field v, which is a function of position r, which is a vector, and time t, and then the components of v can be written in terms of u, v, and w, the three velocity components. So u, v, and w are scalar quantities in this expression. That's the most general form of the velocity field, if you will. The acceleration vector a can be written as the derivative of this velocity vector field. So it is simply I hat as a constant, so I can slide the derivative operation past the I hat times du dt plus j hat dv dt plus k hat dw dt. I can use calculus chain rule and write this out explicitly. Du dt as since u depends on x, y, z, and t, I can write this as the partial of u with respect to t times dt dt, partial of u with respect to x times dx dt, same way dy dt, and then dz dt, right? The interesting thing is the dx dt, dy dt, dz dt are nothing but the x, y, and z components of velocity, which are u, v, and w. So that's the simplification I've made over here, right? So in other words, the acceleration vector A is simply equal to partial of u with respect to t plus this v dot del operating on u. And remember, this is simply the x component of this velocity vector that I've written over here, right? And again, just for your reference, the del operator is simply defined as, remember, this is the defining equation, as I hat d dx, j hat d dy, and k hat d dz. In general, A is a velocity vector, and so it's dv dt, and so I got to apply this operation, if you will, across all three components, and that is compactly represented by this result. It's the partial of v with respect to t, v being a vector, then it's the u multiplied by the partial of v with respect to x, again v being a vector having three components, likewise v and w multiplied by the relevant partial derivative terms as well. And so a compact wave is basically this one now in 3D becomes this, right? So this is simply, remember, the x component, but when I express it as a 3D component, it is this expression right here. The difference being, instead of u, I have the velocity vector, and then instead of u over here, I have the velocity vector. All right, so I've copied this one more time onto the next slide. And just a quick comment, some books, not our textbook, they sometimes introduce a special symbol for the material derivative, also called ddt, with an uppercase D, but we don't use that here. And let's interpret this expression by looking at the flow through a nozzle, right? So if I have a flow through a converging nozzle, imagine I have fluid like water going through. And if I park myself at a fixed location, that means position is fixed. I'm allowing things to vary with time. That's what this term represents. The partial of v with respect to t is keeping the position fixed and asking the question, how does the velocity at that location change as a function of time? So this term has a name. This is called a local acceleration. And the word local is used because the position is fixed. And the second term is v dot del operating on v is what's called a convective acceleration. Okay, so this particle could be here at a later time, this particle could be here, and at a later time it could be here. And since here the diameter is larger, velocity will have a certain value. Since it reaches here, it's a smaller area, the velocity is a higher value, and it reaches here, the velocity is, the area is even smaller, the velocity even still higher. So the fluid particle experiences an acceleration as it goes from this station to this station to this station, right? That process, or that phenomena, is expressed through this convective acceleration term, which is made up of these three terms in the Cartesian coordinate system. So again, to summarize, the material acceleration has two components, and I always use this nozzle example as a way of interpreting what do I mean by two components of acceleration. Is what's called local acceleration, and keep the position fixed and ask the question, is the fluid velocity changing at that location? And then the convective acceleration is as I move downstream, in this case downstream is the term I'm using, as I move from a wider section to a narrower section of the nozzle, is the fluid velocity increasing. And in this case you can see the fluid velocity is increasing, and so that's caused by the convective acceleration term.